Howdy, and welcome to section 9.1, 9.2, where you get to look at chemical equations and actually make sure that you're not losing stuff. I mean, there's this incredible law called the law of conservation of matter, which says that total mass of your reactants must equal the total mass of your products. You can't suddenly have more atoms of something on the reactant side of an equation and less on the product side. That's just not the way nature works. So to get your head around this, I highly encourage you to have three lovely little worksheets that go with this section. I'm going to go over the answers to these later in the video, but it would be a whole lot better educational experience if you try them for yourself. First one is counting atoms and molecules. Do a little math. As I said, the mass of the reactant side, zinc plus hydrochloric acid, has to equal the mass on the product side, zinc chloride plus hydrogen. I think you can do the algebra, but like I said, I'll go over this at the end of the video. By the way here, this is one of these examples of the sins of the past catching up with you in the present and the future, because if you do not know how to write chemical formulas correctly, all of these masses are going to be messed up and you are not going to be able to balance equations. So if you need some help with balancing chemical equations or writing formulas, make sure you're making time to get some help and do that sort of thing, right? So, okay, so this was the second one. And the last one, balancing chemical equations. Here your textbook has a particular methodology they recommend for balancing chemical equations, and there are many ways of doing it. If you don't find thinking it through step by step in the steps that they've done it, then feel free to do it any way that works. The bottom line is the equation balance. So this is actually a wonderful section because everything is self-checking. In order to know that you have a balanced chemical equation, all you have to do is add the number of atoms on each side of the equation, and voila, it's either right or it isn't. So I'm going to zip on to a little presentation, a balancing chemical equation tutorial. It's on the computer. This was something that I made like a long time ago. You will have to do it on your own, but I'll give you the first few pages just to give you the idea of what balancing chemical equations is all about. I have saved this ancient piece of technology simply because I had my daughters do some of the audio in it, and it's just kind of fun for me to hear my 8-year-old daughter talk about balanced chemical equations and the rest. So we'll get back to the answers to these worksheets in a moment.
This is a balanced chemical equation.
So what can an equation tell you? A great deal. It can tell you the reactants and the products. Water is the reactant, the products are oxygen gas and hydrogen gas. It can tell you the state of both the reactants and the products. This little L here stands for liquid water, the G, gaseous or oxygen gas and hydrogen gas. S would stand for solid if we had one. It also tells you the number of atoms and molecules. 2 molecules of liquid water decompose to form 1 molecule of oxygen gas and 2 molecules of hydrogen gas. Okay, the really cool thing is this is a balanced chemical equation. We have 4 atoms of hydrogen, and 2 times 2, 4 atoms of hydrogen. 2 atoms of oxygen, and 2 times 1, 2 atoms of oxygen. This big 2 is called a coefficient, just like this 2. You're not changing formulas, you're just saying how many molecules of water you have. Coefficients.
This is an unbalanced chemical equation.
So if you count oxygen on the product side, we've got 2 atoms. Oxygen on the reactant side, we have 3. That defies the law of conservation of matter. So we have to use coefficients to fix it. So the solution, put a 2 coefficient in front of potassium chlorate, 2 in front of potassium chloride, and a 3 in front of oxygen gas. We now have 3 times 2, 6 oxygen atoms on the product side, 3 times 2, 6 atoms of oxygen on the reactant side. So again, when you go through this on your own, make sure you follow the procedure. Get it clear in your head. What you're looking for here is just to make sure that the total number of atoms on the reactant side equals the total number of atoms on the product side. You can set up a little table like this. A lot of people like to do it that way, just to make sure you don't lose track of things. There are little clues and little hints that you basically learn shortcuts as you go along. But quite honestly, I will spend 20 minutes balancing some equations. There is no shortcut. It's just perseverance, patience, and I know you have a lot of that, right? So, here's an equation for the reaction of zinc oxide reacting with hydrochloric acid to form zinc chloride and water. It is not balanced. I'll show you. So, how many zinc atoms on the left side? Let's ignore that 2 there for now. That's not supposed to be there at the moment. How many zinc atoms on the left side? I'd say there's 1.
Yes.
Very good. How many oxygen atoms on the reactant side? 1.
Yes.
How many hydrogen atoms on the reactant side? 1.
Yes.
How many chlorine atoms? 1.
Yes.
And like I said, that 2 is like a little misprint there. That's not supposed to be there at the moment. So it will be eventually perhaps, but not at the moment. How many atoms of zinc on the product side? I see 1.
Yes.
How many oxygen atoms on the product side? I see 1.
Yes.
How many chlorine atoms? 2.
Yes.
How many hydrogen atoms? 2.
Yes.
So notice that the number of hydrogen atoms and chlorine atoms are not the same on the left and right sides of the equation. 1 on the reactant side, 2 on the product side. We have to enter a coefficient in order to make that equal. And the coefficient would be 2. That's why that big red 2 is up there. Hopefully it goes away. You go to another equation. By the way, you have to attain a certain score here in order to get beyond this page. If you don't, then you have to go back and start all over again. Make sure you exit. So the above reaction is balanced. I got 1 potassium, 2 bromine, 1 bromine. So the answer is false. Potassium is a reactant? Yeah. There are 2 atoms of bromine. I see 2 there and 1 there, so false. Potassium bromide is a product. Yes, it's on the right side of the equation, so that's true. Bromine is a liquid reactant. Yeah. The equation may be balanced by adding subscripts to the right of 2 of the elements. Absolutely not. You can never change any of these little subscripts. Those are parts of the actual formula. You can't change the formula, so that is false. Then you have to balance the above equation by placing the correct coefficients. If I put let's see, we got 2 bromines here. We need 2 bromines on this side. But now we've got 2 potassium, so I better put 2 on this side. Score my equation. Whoa, I just got 3 marks. Check to see if you've got high enough to keep going. Mastery indeed. Give yourself a hug and then move on to the practice section. So here is the practice section, and I'm going to let you do this on your own because we want you to have the practice. I can give you a paper version of this. This will work so much better for you if you try it first on paper. Make sure you talk to me and get the paper version. These are all worth like a lot more marks than that stuff at the beginning. So if you find your score drops by 5 or goes up by 5, that is the way it is supposed to be. So, just in case you're wondering, there are certain things you should be doing here in order to master balancing chemical equations. I would start by watching the videos. See the little folder on Dynamis that includes the videos. Watch all 4 if need be. If you can do it by watching 2, then that's cool as well. Move on to the balancing equations tutorial online. You might want to get in the habit of printing up some of these scores just in case you don't like what you see in Dynamis, because I'm going to take what I see in Dynamis, and if you say it's something different, I'm going to have to go with what's on Dynamis. So it's not a bad idea to occasionally print up your scores. So the only point I'm making really here is watch the videos. And this, of course, is true for every section, not just this one. Okay, counting atoms and molecules. I don't think you're going to find this terribly challenging, but this is the kind of thing you're mentally doing in your own head when you are balancing a chemical equation. You're looking at each of the reactants, and in order to do that, you need to make sure you know how many atoms are in each molecule and how many molecules are in the equation. So when we look at a nice formula here for C3H8, which you immediately recognize as organic, 3 carbons, I think that there's propane. How many molecules of propane do you have? I see 1 molecule of propane. How many atoms of carbon in propane? No subscript 3 tells you you have 3 atoms of carbon. How many atoms of hydrogen? I see a subscript of 8. Then moving on to number 2, potassium chlorate. How many molecules? I see a coefficient of 2 in front of the formula. That coefficient tells you you have 2 molecules. And again, make sure you never change these little numbers, the subscripts. That's a no-no. The only thing you can do in this section is add coefficients, these numbers in front of a formula. How many atoms of potassium? 2 times 1 makes it 2. How many atoms of chlorine? 2 times 1 makes it 2 again. And how many atoms of oxygen? 2 times 3 makes it 6. I'm going to let you finish the rest of those just so you feel really good about what you're doing. And then if you have any questions about that, do make sure you check with me. I'm going to post the answers at some point in the classroom and you can just check for yourself. But I don't think you need to see me do the rest of it. So that's good on that one. Okay, moving on to using the law of conservation of mass. You have this sheet, and again, I would encourage you to try this on your own before just simply looking at the answers. The idea, of course, again, is we're looking at evidence that the law of conservation of mass is in fact true. If we have 65.4 grams of zinc as a reactant, and then we have 72.9 grams of hydrochloric acid that we're dissolving the zinc in, we're going to get a chemical reaction and form some hydrogen gas, 2 grams of it, and zinc chloride. The question is, how much zinc chloride? Well, this wonderful law of conservation tells you that whatever you have in the way of number of atoms or the mass of reactants has to equal number of atoms and the mass of the product. So 65.4 plus 72.9, if you add those two together and subtract 2, a little bit of algebra, you should get something like 136.3 grams of zinc chloride. Makes sense? Makes sense. We are looking at sulfur, 256.5 grams, and then we're adding oxygen to it. This is a combustion reaction. We're basically burning sulfur in air, and the oxygen is combining with sulfur to form a gas called sulfur dioxide. The total mass is 512.5. So we now know that if we subtract 256.5 from 512, we will get this missing quantity, this mass of oxygen. Could be wrong here, but I'm thinking that's another 256. 256 plus 256, 512. Makes sense? Makes sense. Okay, number 3. Magnesium and fluorine gives magnesium fluoride. A plus B gives C. What the heck is A in terms of its mass? Again, the algebra tells you that C is equal to A plus B. So in this case, we only know what B is. So 62.3 minus 38.0, 24.3. There you go. I would suggest that you try the rest of those on your own, and then if you have any question about the correct answer, I highly encourage you to talk to me about it. Okay, the final one in this 9.1, 9.2 section is balancing chemical equations, and that's actually, of course, what we're after in this section. Can you take an equation like number 1, which is not balanced, right? I've got 2 atoms of copper on this side, 2 on that side, but look at my oxygen. I got 2 atoms of oxygen on the reactant side and only 1 on the product side. So immediately I say to myself, that's not balanced. That defies the law of conservation of matter. So the procedure here is something that not everybody actually would go through this for every equation, but in one way or another, essentially this is what your brain is doing. You're looking at each element, and I'll just work through one here for you just to see how it would be done this way. There are other ways. You could make up tables for reactants and products and just list each of the elements and come up with the atoms, but in this case, this is one way that your textbook suggests you use. How many copper atoms are in the reactants? Well, now I see 2 right there. 2 subscript, and then I look over here at the copper, I see 2 again. So what coefficient, again this is a whole number that you would put in front of the equation, will make the number of copper atoms in the reactants and products equal? They're already equal, so I would write some sweet little word like none. Move on to sulfur. So sulfur, how many sulfur atoms are in the reactants? I see 1. How many sulfur atoms in the product? I see 1 again. What coefficient will make the number of sulfur atoms in the reactants and products equal? They are equal, so none. We don't have to add anything. But now it gets interesting. How many oxygen atoms are in the reactants? I see 2. That's what that subscript 2 tells you. Then in the products, I see 2 there, plus 1 here. Wow, that makes 3. Now things get a little more complicated. What coefficient will make the number of oxygen atoms in the reactants and products equal? I say that we need a 2. So again, it's going to depend where you do this. And then once we put the 2 in, I'm going to suggest that we have to change a bunch of the coefficients, so the answer would be yes. I'm not going to rewrite the equation, I'm just going to balance it for you. In order to make sure we end up with the correct number of oxygen, I put this 2 in here, 2 sulfur dioxide. Now we have 2 times 2 is 4 oxygen plus 2 is 4. Sorry, 2 times 2 is 4. At the same time, I've got an oxygen there. What if I put a 2 there? Now I've got 2 and 2 is 4 oxygens. Let's check copper. 2 times 2 is 4. On this side we've got 2, so I'm going to put a 2 in front of the copper sulfate. One problem here. Oxygen is not working for us, so the only way I can make that work is I've got 3 times 2 is 6 oxygen now, 2 here and 4 here, 6. So check everything, and again, the benefit of a balanced chemical equation is you can check these for yourself and actually make sure they are accurate. So 2 times 2 is 4 coppers, 2 times 2 is 4 copper. Copper is balanced. Sulfur, we've got 2 sulfur on the reactant side, 2 sulfur on the product side. Moving on to oxygen, 3 times 2 is 6 oxygen on the reactant side, 2 oxygens here plus 2 times 2, 4 oxygens here, 4 plus 2 is 6, 6 and 6 is equal. Again, I don't necessarily think all of this is necessary because ultimately you're going to end up basically trial and error. Highly recommend you use pencil for this sort of thing because chances are by changing one, you're going to have to end up changing the other one. I will show you the answer to the next one. You might want to try it first. Again, this is pentane, and yeah, whatever method you work at that ends up with a correct balanced equation, that is absolutely cool. As I suggested, you don't necessarily have to fill in the rest of that sheet as long as you can balance this equation. That's really what we're after. Try it on your own though first. Look at the fact that you've got 3 carbons on the reactant side but only 1 on the product side. Got 8 hydrogens on the reactant side but only 2 on the product side. So take your pencil out and try a little trial and error and see if you can come up with the correct answer. I'm about to put the correct answer in, so if you haven't tried it yet for yourself, you might want to stop the video. But if you manage to get the following, I would say you know what 9.1, 9.2 is all about. So here we go. You should have a coefficient of 5 oxygen molecules, which is 10 atoms, right? And then on the product side, we're going to need a 3 coefficient there and a 4. And like I said, you can check this for yourself. 4 times 2 is 8 hydrogen, 8 hydrogen. 5 times 2 is 10 oxygen. 3 times 2 is 6 plus 4 is 10. 3 carbons, 3 carbons. Voila, we are good.